Welcome back to Uniform Text. Today we're doing another physics problem. This is again from the Discord server. I'll post a link in the description. So a candle is flowing stably in water due to aluminum cylinder of equal radius that is glued right under the bottom of the candle, right? And the length of the cylinder is 1.0 centimeters, and the density of the candle, aluminum, water are 0.8, 2.7, and 1.0 grams per centimeter cubed, respectively. So for part A, I want to find what is the maximum and minimum length of the candle such that it can float stably in the water. So for the minimum length, that's pretty simple, right? Just set buoyant force equal to your total mass. So let's do that. You know the formula for buoyant force, right? So formula for buoyant force is just going to be the density of the liquid it's displacing. So in this case, water times G, and then the volume that's displaces, right? You want to set buoyant force equals to the mass, your weight, right? So it's mg, total mass and total G. So you can see, you can cancel the G right away. So we get rho V is equal to m, right? So now you take the rho out. Now your volume, right? Let's set the cross-sectional area of this candle to be A, right? So the volume of the bottom part is just going to be A x, right? This is defined to x, and the top is going to be length L. So AX plus AL. It's going to be equal to your mass. Your mass is just going to be your density. Mass is equal to just your density times your volume, right? So it's going to be your density. So density of aluminum times your volume. So that's aluminum times your A times your X plus your density of the candle times your A and times L this time. Now we see have A on every term both sides. So just cancel A out. Bye-bye, 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 bye-bye. Now you expand this, you get rho x plus rho L is equal to rho aluminum x plus rho candle L. Now to solve L, let's just put rho A x, right, minus rho x, right? Then just put this on the other side, so rho L minus rho candle L. So isolate L and just get rho minus rho C, right? Rho candle. And now you get just evaluate this with rho A being 2.7, rho being 1, x being 1, rho C being 0.8. And you get L is going to be equal to 8.5 centimeters. So that is your minimum. Now for maximum, you want to think about how it can float stably. So think about the center of mass and where the buoyancy acts on. So let's draw two diagrams on a tilt, right? So you see one candle here. Okay, I should draw on a tilt, my bad. I have one candle here, the aluminum part here, another candle here, aluminum part here. See, if the center of mass is here, it goes downwards, right? Now the buoyant force can either be up here or upwards or down here, right? So because the weight is always on the center of mass, it will contribute no torque, right? So just cancel that. You can see if it's on top, then it will cause the candle to topple back up to equilibrium, right? It will go back to being a straight line. But if it's on the bottom, see, it will continue turning this way and it will flop. So this is not stable. You want the place where the buoyant force acts be above the center of mass, right? So then to find the maximum height, maximum length of the candle, just set these to be equal, because that's the critical condition from when it goes from stable to unstable. So let's first find the center of mass of the candle. For this purpose, I'll set the bottom, the aluminum will be at y equal to 0. So your center of mass, your y center of mass is going to be bottom, right, 0. But center of mass of this piece is x over 2, right? So first your mass, so mass is going to be rho A times your area times your x times the height away from your origin point or reference point, so x over 2, plus the mass of the candle, big candle, so rho candle, area, length, and the distance away from origin, which is just x, plus this will be the midpoint, right? So just L over 2. Right, this all makes sense. Nice, okay, good. Now you know the formula, right? The formula is just, for center of mass, is just mass this times distance plus mass times distance over the masses, the sum of the masses, right? So this will be both masses, the sum. So rho A area X plus rho C area L, right? So you can just cancel out A again. So rewriting this equation, since it's getting a bit hairy with the variables, I'll just plug in the values when I can see them. So rho A is 2.7 divided by 2 as 1.35 x squared. This is going to be 0.8 Lx, x is 1, x is 1, right? So just plus 0.8 L, I just rewrite that, 0.8 L, 0.8 divided by 2, that's 0.4, then L squared, right? And now at bottom for this is 2.7, right? X is 1, so 2.7 plus 0.8, I mean 0.8 L, 0.8 L. Yes. Okay, now we want to find where the center of buoyancy acts on, right? So only counts after this, so we don't take care of this part. So just let the length of the candle submerged under the water be, let's just call it random variable m, let's say. So you want to find same thing here, right? So rho v, go from this point, equals to m. Except here, your volume is going to be m and x, not L and x in this case. So we can just, we know that A is going to cancel out, right? So just not write that in the first place. So it's going to be x plus m is equal to the mass, but mass is going to be a whole thing. So it's going to be rho aluminum x plus rho candle and length, right? Because that's going to be the whole thing. Now we can find the m. So let's put rho m here. It's going to be equal to rho A x minus plus rho CL minus rho x, right? Now we can just plug in the numbers. We know rho is going to be 1, right? So just get rid of that. So rho A is going to be 2.7, x is going to be 1, so 2.7. Rho C 0.8 plus 0.8 L. Rho is 1, x is 1, so minus 1 divided by 1, right? So this is your m. You can write as 1.7 plus 0.8 L. So you want to set, no, not quite. You want to set total length is going to be m plus x, right? So you want to set m plus x divided by 2, so the center where it acts be equal to this thing. So have this formula, 1.35, 1.35 what? We have x squared, so just x squared is 1, right? So just cancel that, just 1.35 plus 0.8 L plus 0.4 L squared, right? Yeah, 0.4 L squared. What's on the denominator? Let's see, 2.7 and 0.8. 2.7 plus 0.8 L, right? I want to set this equal to your m plus x divided by 2. Well, x is just 1, right? So just cancel this. So it's 2.7 plus 0.8 L over 2, right? So 2.7 plus 0.8 L over 2. And now you can see, if you can just cross multiply both sides, get rid of the denominators, you can see this is going to be a quadratic, and this times this is also going to give you a quadratic. Then you can just subtract them and set it to 0, and you can solve for L. So I trust you can solve for L yourself. So the final answer after you solve for L, because it's just a simple plug-in into calculator problem. So L at the end is going to be 18.547 centimeters. And this is your maximum, because this is based on the concept of this, right? You understand? So now for part B, the candle is lit such that it consumes wax at a rate of 1 millimeter per minute. If the initial length of the candle is 12 centimeters, how long will the candle float in the water? So this is just a simple question. So 12 centimeters, you can float until it's 8.5 centimeters. So 12 minus 8.5, it's going to be 3.5. But it's in millimeters, right? So just times 3.5 times 10, that's going to give you 35. So 35 minutes. And we're done.